A very good afternoon to you all, and welcome to the third session of this series, Geoprocessing using Python. Right, yesterday we discussed in detail or briefly we discussed about the basic constructs of Python programming language. So, actually, when you work on geospatial data, you need not know entire thing about Python programming language. So you can say that geospatial processing is just a subset of Python programming language what we will be using. Right. So yesterday we discussed in detail about how do we create variables, how do we manipulate variables. Then we discussed about different data structures like how do we create list, dictionary, or set data structure. Then briefly I touched upon how do we read and write a text file. Right. So today we will continue on the same journey. Now today I will introduce you two fundamental libraries in Python programming that actually almost any data science application which you are building or any data science library if you use these two libraries are the foundations of, you can say, the foundations of data science applications in Python programming. So I'll just briefly touch upon these are two libraries. So these libraries actually we will be using further in our course, like when you go about raster and vector data processing. So the most fundamental library is Numpy. So Numpy stands for numerical Python. That is a library for handling matrices, or you can say the one dimensional, two dimensional, n dimensional uh, and n-dimensional matrices. And the second library is what I will briefly touch upon is matplotlib. So that is basically for visualization. So actually the most of the contents of this lecture I have taken from this link. So you can just go through that link. That is very nice documentation available there. So most of the contents I have taken from there. So if I briefly read about NumPy, so NumPy or numerical Python is an open source Python library that is used in almost, as I said, in every field of science and engineering. That what you use with Python, right? So it's a universal standard for working with numerical data in Python, and it is the core of scientific Python and entire data ecosystem. So any data science library or any machine learning, deep learning, they are built on the foundations of, say, NumPy. Plus, NumPy API is used extensively in Pandas, SciPy, Matplotlib, Scikit-learn, Scikit-image, and most other scientific and data science packages in Python. So the NumPy library contains multi-dimensional arrays and matrix data structures. As we said that NumPy is for for handling multi-dimensional arrays. No, you are not just limited to one, two, or three dimension. You can handle a million of, if your data contains million of dimension, that what you see in deep learning or machine learning applications. So those data also can be quite easily handled with NumPy. So the basic class in NumPy is called what we call ND array. So it provides an ND array, a homogeneous n dimensional array object with methods to efficiently operate on it, right? So ND array is the basic class which will provide us construct, like list was a construct which was allowing us to store multiple values in a variable, right? So similar to that, NumPy or ND array is a construct that allows us to store and manipulate, like to store the data in n-dimensional format and efficient methods to operate on that data, right? So NumPy can be used in a variety of mathematical operations. So like whatever mathematical operations you do on matrices, that can be can be done quite easily using NumPy's this ND array class, just with a few set of commands. Like you need not write complex loops like you are right we do it in other programming languages. You need to just write a single instructions on, and that works on the entire array, right? So like this is the basic structure of NumPy array as we discussed yesterday. List is just a list, as we discussed, list is an ordered collection of number, or you can say that a variable that holds more than one value, right? So when we are storing list as a single index or single dimension, so that we call one dimensional array, right? So when we are arranging those numbers or variables, say in form of rows and columns, right? So that what we call two-dimensional arrays. Like here you can say that these are different two-dimensional arrays. Now when we stack together more than when we stack together multiple two-dimensional arrays. Like here you can say that here now we have stacked together three two-dimensional arrays, right? Now this is what we call three-dimensional array. Now similarly we can keep on adding new and new new to this. Like when we stack multiple three dimensions to array together, that we call four-dimensional array. Then if we four-dimensional array, if you stack together, that we call five-dimensional array, and so on. Then this is an extendable idea. Like we can go to n dimensionals. So the most important thing is like when you are accessing an element from a one-dimensional array, right? So then at that time we just need an index, like we were saying, a single index, like we were saying in list. So if you want to access any element from the list, because all elements are stored in a sequential list, like so, like I can extract first element, second element, third element, fourth element, fifth element, and so on. So I need just a single index to extract or retrieve any value from my list. When I am arranging the data in a matrix form or say two-dimensional array, at that time we need two indexes to access any element uniquely. Right? So one we will need row number, and second element we need its column number to fetch the value. So so similar with this, this concept also extends when we want to extract a unique value from a three-dimensional array. That time we need three indexes. One is like from which stack to pick up, then second in the again row number and column number. So similar to this is an extendable idea. So as we said that yesterday, like if you are working on your local system, then once you are then first thing you need to install NumPy into your system. So I think like yesterday I introduced you an environment or package manager called Conda. So just with the help of Conda, you can install Conda, install NumPy, or even if you are working with pip. So with pip also you can install pip NumPy. But anyway, we are working in Google Colab. So in Google Colab, this library already comes installed, pre-installed, right? So otherwise, you can install it by Conda install NumPy or pip.that install NumPy. So now once the library is installed to your system, as we discussed yesterday, that by default all functionalities of the Python or all libraries which are available in the Python does not come to the interpreter automatically when you start interpreter 4. So if you want to use it, then you need to import the particular library. So how do we import NumPy? So this is a standard convention generally people use, import NumPy as NP, right? So import NumPy is good enough, but what happens? So whenever you want to access any function inside NumPy, then you need to write like NumPy dot. So with this construct, what we are doing, like we are just making a shorthand for NumPy. So this is a convention generally what people use. So import NumPy as NP. So anytime now I want to access any element or any function of the NP library, then I need not type entire NumPy, right? I can just refer it using NP. So this means that I am subsequent in my code, I will be referring any function or NumPy as NP. Like that, it saves us from a lot of say typing, right? No, so now then I'll talk about this this way. I'll be talking now. Suppose if you want to create a list, like as we said that suppose if you want to create a one-dimensional array, like an array which has a single dimension, like where you need a single index to access any element of array. So like yesterday we discussed the function range, right? So range, if you pass it a number, it was generating a sequence. So equivalent of range in NumPy is a range, or what you can say array range, right? So what it does, it creates a range of numbers like from 0 to 5, and arrange can create a one-dimensional array out of that. Like if I type a is equal to np dot a range 6, and if I just try to print a, you can see that it created an array with 6 values. So this looks like quite similar to the list in Python, but it is more specialized form of list. You can say that it is a list specifically for handling numerical data. Now, if you just read about what are the differences, what is the difference between a NumPy array and a list? So NumPy gives us an enormous range of fast and efficient ways of creating arrays and manipulating numerical data inside them. So you can say that NumPy arrays are specific class of list. You can say that that is specifically made for handling enormous range of fast, like for handling the numerical data quite efficiently, right? So plus it offers us enormous range of fast and efficient ways of creating those arrays and manipulating those arrays. Like, right. So as you said that Python lists are quite generic in nature, so they can handle a different kind. They are generally they are made for generalization. So NumPy lists are a specialized list, so like they are specifically built for handling numerical data. Right, so NumPy arrays are much faster and more compact than the list, because as you said that Python lists are quite generic in nature. Because of generosity, there will be some trade-off, right? So they will be like you can do a whole lot of operations in Python lists, but they are because of their general purpose, so they are relatively slower compared to NumPy arrays, sorry. An array consumes less memory and is more convenient to use. NumPy arrays are slower than the list when you append elements to the list. Right, so this is one limitation of the NumPy arrays. Like once you created a NumPy array, you cannot, like, so there are ways to change the size of the array, but in generally it is not recommended to change the size of your array once you create it. So whenever you so so whenever you want to, so this is the only disadvantage, like NumPy arrays are slower only when you want to append elements to the NumPy array compared to the list. Otherwise, for numerical data, NumPy arrays are much faster than our normal Python lists. Right, so now let's start with basic two arrays. Anyway, we have talked in detail about it. So you can say that an array is the central data structure, as list, dictionary and other things. So an array is the central data structure of the NumPy library. So that is a class ND array. So array is the central structure of the NumPy library. Array is a grid of values. You can say a grid of values. So that grid can be a long one-dimensional grid, two-dimensional grid, or three-dimensional or n-dimensional grid. So an array needs to be indexed by a tuple of integers, or you can index by boolean, or there are many other ways of indexing an NumPy array that we will see with examples, and it will be more clear. So there is one term we use, the rank of an array is the number of dimensions the array has. Like if your array is one dimensional, then we say, so this, we must not confuse it with the rank of a matrix. So in the parlance of NumPy, we say that the rank of an array is the number of dimensions in that array. The shape of array is the tuple of integer that gives the size of array along each dimension. So when we refer to the shape of a NumPy array, so we are referring to that, like how many elements are there along axis 1, how many elements are there along axis 2, how many elements are there along axis 3, and so on. So now let us see how do we create one-dimensional array. So one-dimensional array are also called vectors, right? So as already we have seen an example of a range, but now suppose if you want to create a one-dimensional array, or say vector, suppose if you know already, like I want to create a three-dimensional vector or four-dimensional vector, or say the vector with 4 values, right? So that you can just create by calling the function np.array and pass it a list of values separated by a comma. Right, so if I pass it np a equal to np.array 1, 2, 3, so what it does, it creates a NumPy array like this, np array 1, 2, 3, or you can say that it is like this only. Now actually we have, this is a single dimensional array, right? Because it has, now for accessing any element of this, we need just a single index, like item number 1, item number 2, item number 3, or 4. So if you call np.array and pass it a list of values, it creates a one-dimensional array for us, right? So as we can say that NumPy arrays cannot grow the way a Python list does. As you said that NumPy arrays are much slower compared to the Python list when you want to extend its size. So no space is reserved at the end of array to facilitate quick appends. So it is a common practice either to grow a Python list and convert it to NumPy array. This is the most convenient way. Like if you want to keep on appending or extending your NumPy array, so this is like you just maintain a list side by side and you just keep on adding elements to that list and then convert that list to a NumPy array, right? So now similar to like there we created an array with this specified fixed element. Now suppose if you want to create a one dimensional array, say with all zeros, and like I want to create a array with 3 elements and I want to initialize all of them, say value 0. So there is a function called np.zeros and you pass it 3, and second argument actually you can specify like in which what data type you want to use for storing that value, right? So suppose I write integer, so now all elements of my one dimensional array will be integer types. So np.zeros, if I create, so it will create an one dimensional array like this where the data type will be 32-bit integer. So similar way, suppose if you have already created an array and you want to create an array of similar shape and size, right? Like suppose if I have created an image, or image generally is represented as two-dimensional array. Now suppose I want to create an similar image like the image which has same width and height, but I want to fill that array with say different values, right? So sometimes that requirements might be there. So for that there is a function called zeros underscore like. So what it does, so it will create an array of same shape and size as our array A, but it will fill them with the values zeros. Right? So here because our A whatever we created was having 3 zeros only, this was one dimensional array. So if I call np.zeros like, so it will create an array with 3 elements and fill all of them with zeros. So similar to zeros, there are many other counterparts of zeros like zeros, ones, empty, full. So like full creates an array with all values fixed to the fix 7. Like suppose if you want to create ones, all an array with all values 1, np dot ones, np dot empty with very low values, then np dot full 3, 7. Like create an array of 3 elements with every value of that to be 7. So there are some counterparts. There are counterparts of all of these functions as well, like zeros, like ones, like empty, like full, like. Right. So suppose if you want to copy uh, or create an array of the same structure of a given array, like your np dot full likes a comma 7. So what it does, it will create a array which has same shape as our array A, but it will fill all of that element using by the number 7. Right. So like there are so many functions available there. So similar ways, I like as we have discussed. Suppose if you want to fill your array with a monotonic sequence like equivalent to range, there is, as we have discussed, there is a function called a range. So a range, if you just pass it a single number, so it will start from 0 and go up to n-1. If you specify start and stop, it goes from start to stop -1. Then like step size also you can specify like 1 to 6 and go in the steps of 2. And so there is another function called line space or linear space that you want to specify, like suppose generate a sequence from 0 to 10 and 10 such numbers you just to generate. Like here you need not calculate the delta between two numbers. Right. So here to np.linear space, what we need to specify? We need to specify start, end, and how many numbers you want to generate in the series. Right. So it goes from starting to ends, and the delta is calculated automatically. Like here we have specified 0 to 0.5 and go into and generate 6 numbers. So it has generated 0, 1.1, 3, 4, 0.5, and 6. Right, then now these are the examples of a range. Anyway, we have already seen a range 2, 6, a range 1, 6, 2. If I say it starts from 1 and goes on incrementing by 2. But right, so like this, there are different functions. Like these were the issues with the a range function when you use them with numerical values. Actually, basically, a range generally is used for handling numerical data. But so there was like when you want to use it with floating point numbers, it gives an error. Like suppose if you want to generate a sequence from 0.5 to 0.8 with an increment of 0.1. So what happens if you want to if you will use a range, it will just generate up to 0.7 only. And so otherwise you have to give it up to 0.9. Sometimes it might not be readable. Then if you give it up to 0.5 to 0.75 in range of 0.1, either you can do this way or you can. So but this is a better way that you use line space. Right. So like these are something unreadable. So similar way, suppose if you want to generate random numbers, right? So random numbers from a uniform distribution. Suppose if you wanted to generate, like you want to generate the numbers in the range 0 to 10 from a uniform distribution, right? So then with equal every number coming with the same probability, right? So that you can use rand init function. So it generates the random number in the range sequence 0 to 10, and such three numbers is like it creates an array of threes. Then like if you want to generate generate with uniform probability number in the range 0 to 1 only, then you don't pass this starting and ending numbers, so that it will generate the numbers in range 0 to 1. So similar way there are other things. Then suppose if you wish to generate the numbers from a normal distribution, right? So then there are functions like random dot normal, where you specify the mean and sigma of your distribution, and the numbers will be generated from the given distribution. Like suppose if I want to generate three random numbers from the distribution, say with distribution with a normal of 5 and sigma of 2. So like this, you can, there are multiple functions which we can use for generating these numbers. So like this, there are other functions, like there is another or you can say another a function inside NumPy for generating random numbers, that is like RNG. So that is offers a much better control than the random library. So this also can be used similarly for generating random numbers, right? Now the next thing comes once our NumPy array is created. Like, so how do we create arrays? So then finally we must be able to extract the values from the array, right? For manipulation or extracting some useful information. Like suppose I want to know which element is stored at the element at the location number 5, location number 10, and so on. So for that, NumPy arrays, once data is in the array, NumPy is brilliant at providing what you can say easy ways of giving it back to the creator. Like suppose if we create an array like this, like an array with values 0, 1, 2, 3, 4, and 5. As we discussed yesterday, as similar to the list, every element of array will have an index, because this is an one-dimensional array. So we just need a single index to access any element of this array. Like these are the indexes 0, 1, 2, 3, 4, and 5. Now suppose if I want to extract, so as we can see that the indexes are starting with 0, right? Now suppose if I want to get back the second element of my list, so I can specify it like my name of my array, then inside square brackets the index number. Like if I want to access second element from my list, so I will pass A1. Right, now instead of only one element, suppose if I wish to extract some 2 or 3 consecutive elements, right? Suppose if I want to extract second, third, and fourth element, you can say, right? So then I will specify like my name of my array, then static index colon end index. Like it goes from starting index to end -1. So it picks up second element, second means third, second index I will be using, like second means actually it is third element, but we will say that now I will be using index number. So second and third, right? So as we said, as we discussed yesterday, that NumPy indices start from the right to left. Also we can use negative indices also, like rightmost element has index -1, like this 5 will have index -1, 4 will have index -2, -3, -4, and -5. So similarly you can start give negative indices also, like by for slicing. Like see, if say a -2 colon. So if the element on the right side is missing, it like this array indexes goes from the start to end. So -2 to, so this will be -2 to end. So 4 and 5 are printed. And suppose if you specify, like if you miss both of them, like a colon 2, so it means scan entire list from start to end and pick up every alternate element. So by default, what it is picking, like here I have specified A2 colon 4, it is picking every element. Right, now suppose if you want to pick up alternate elements, you can specify it like this as well. And suppose if you want to extract some non-contiguous element, like first element, fifth element, ninth element, 30th element, or then suddenly 25th element, then even you can specify like a list as well inside your indexes as you to your array, like A, 1, 3, and 4. So it will pick up first element, third element, and fourth element. Element with indexes, right? So similar way, suppose if you want to change the content of your array, like yesterday we see in the list. So suppose if you want to make second and third element of array, want to overwrite them with a new value, say 0. So you can specify it like A2 colon 4 0. Then you make this as well. Then you can do Boolean indexing as well. Let's suppose if this is our list, and now suppose if you want to access only the elements which has value greater than 5 in our array. right? So if I write, so there we need not write any fancy loop in the NumPy's parallel. Just write single statement. Like if I write like here, a greater than 5. So I assume here to be is my one dimensional array, right? If I write a greater than 5, so what it does, it creates an array of the same shape and size, but the element of that array now will be binary. Like whenever the value in there will be less than 5, it will be false. If it is greater than 5, it will become true. Like here you can see that if my array A is like this, and if I write an statement like A greater than 5, so it creates an array with these values. Wherever the value of A is greater than 5, so that will become true, and then all others will become false, right? So that this way you can use Boolean indexing as well. Now then there are multiple functions, like you can like you can use that any function as well. Like if you want to check is there any element in my list greater than 5, then you can call the function like np.any my array greater than 5, right? So I need not write any loop for check for the pick up all elements one by one and check if there is any element greater than 5. No. So I just write a single statement like np.any a greater than 5. So if any element of that is greater than 5, it will true, otherwise it will return false. Like similarly, there is a function called all. So np.all, whether all elements are greater than 5, it returns false. Then this boolean array whatever we created by calling this a greater than 5 can also be used as index as well. Like if I pass this array as an input, as an index array to this my a array, so a square brackets a greater than 5, it will just pick up the elements where the value of this internal array is true. So now it just picks 5 and 6. So like the same way, like if you want to initialize, change the values of all these elements to 0, then you can write just a greater than 5 is equal to 0. Then all values will gets replaced by 0. And then you can write ands as well, like if a is greater than 3 and a is less than is equal to 5, change them to 0 and so on. So like actually it offers multiple ways of manipulating NumPy arrays. Right, similar way, there is a function called np.var. Right, so np.var a greater than 5. So np.var, if you write np.var a greater than 5, so what it does, it returns us the indexes of our a where a is greater than 5. Like for this 6, 7, and 6, the values are greater than 5, so it returns the indexes corresponding to this. Like it says that at the index number 5, 6, and 7, the values are greater than 5. Right, like this you can write for assignment also, like a less than 5 is equal to 0. Like where suppose if you want to replace all values which are less than a threshold, like you want to clip all values in image, say, so like all values less than 5, make them 0. Like you can just write the single statement a less than 5 is equal to 0, or you can say like a greater than 5 equal to 1. Like it's like you are doing a binary thresholding. All the values less than 5 we are making as 0, and if all values greater than 5 you just want to make it 1, you can write it like this. And similarly, you want to change them, or there is a function like np.clip, you can clip the values and so on. And all matrix vector operation, like whatever vector operations that are done element wise. Like suppose if you want to do two vectors together, so you can just write plus operator. Like if I have created two arrays like a and b, and if the primary requirement for doing these vector operations is that both the vectors must have same number of elements. Actually, if I say vector dimension, that will be confusing here. So you can say that we'll talk about in terms of number of elements. It's like if you do for doing any vector operation, it should have equal number of elements. So like just I need not write any loop. Like I have an array A with the two values and array B with two values. I will just write A plus B. So element wise summation will be done. Element wise subtraction, multiplication, division, integer division, whatever you want can be done quite easily with the single statement. You need not write anything. And like suppose if you want to do you want to add some scalar to your vector, right? So generally the requirement, as I said previously, that whenever you want to add two vectors together, their number of elements in both of them should be equal, right? But sometimes suppose if you want to add a scalar value to all elements of your vector, so that also can be done So there you need not write like, so suppose this was our original vector one dimensional array with having two elements. Now suppose if I want to add 3 to every element of this array, right? So like I want to offset every element of this my vector with some offset like maybe by 3. So then I need not create an array of say 3 and 3 2 of 3 of 3 and 3 of 2 like 2. So actually that is done automatically internally by Numpy. So this is what we call a type of broadcasting. Right, so here the 3 will be internally expanded to the size of this A. Like this two threes will be copied, and now element wise this 3 will be added to all elements. So like similar way minus, division and other things can be done. So that there are different operations available. Like suppose if you want to square every element of your vector, so double star and 2 square root exponentiation, so many functions are available there. Then suppose if you want to calculate the, otherwise by default it is a dot operator, like element wise two vectors will be multiplied. Specifically then suppose if you want to calculate dot product as well, then if you want to calculate dot product, then you can call dot as well, like np dot dot. It calculates the dot product of two arrays. And suppose if you want to calculate cross product of two arrays, then you can call np dot cross, then sin pi. There are so many functions available that you can just go through the documentation. So min, max, sum, standard deviation, and all a whole range of like whatever numerical operations you can do on one dimensional array, two dimensional array, one dimensional array, almost all operations you will find inbuilt in the NumPy array, right? So now let's extend this idea to two dimensional arrays. So right, so whenever you are dealing with one dimensional array, as we said that we are creating a big list. Now suppose if we arrange our elements in rows and columns, right? So that what we call matrix or two dimensional array. So similar to one dimensional array, suppose if you wish to create a two dimensional array, you just need to create it like this, np dot array. Now every row we need to separate by a comma, right? So there we were just separating all elements just by comma. Here every row we need to create just like a one dimensional array, right? So as we said that when we stack multiple one dimensional arrays together, that what we call two dimensional array. When we stack multiple two dimensional arrays together, with that we call three dimensional array. Like here, suppose if you want to create two dimensional array, like here we are stacking multiple one dimensional arrays together. Like this way you need to create like double brackets you need to use, and every row you need to separate it with the other row by comma, and every row again we need to specify as a one dimensional array, right? So now here you can see that we have created two one dimensional arrays and stacked them on the top of one another. Right, now if I inspect the shape of this array, as we said that the shape of array defines like how many elements are there along each axis. Now this particular array has two dimension, one is rows and another one is columns, right? So it is saying the shape of array. If I say there are two elements in the row, like you can say that there are two rows and there are three columns. So if I see the shape, this is 2 cross 3. So similar to one dimensional, like these zeros, ones and other functions are extendable to one dimension. There you need to just specify the dimensions of as array. Like suppose if I want to create an array of zeros with 3 cross 2, size 3 cross 2, then I will just call np.zeros 3 cross 2 and create like this, np.full, eyes and all. There are so many functions available there. Then similar to one dimensional random numbers, you can generate two dimensional random, three dimensional random numbers, three dimensional random arrays as well, quite easily using this library, right? So now indexing, as we said that now suppose if you wish to index any element uniquely from this two dimensional array, now we need two indexes. First is our row number and second one is our column number, right? Now if I write like here, now I need to pass our array two indexes, one is row and one two. So first row, second column. So first row here I mean that index first, so it will be row number second. So first row and second column, it picks up seventh number. Then similarly like now if I specify a1 comma colon, so it means that a row number 1 and all columns. Like instead of picking the specific column, I just want to pick all columns, like a row 1 all columns. So if I write it like a1 comma colon, it will pick up all elements of the row 1. Like here we are specifying second column and all rows, right? So that will pick up this entire column. Like this you can build fancy indexes for extracting any things from your array. Like here you can see that this is first and second column, all rows. Then this is a second last, starting from the second last column, second last row to uh, all rows, and second column to all, second last column to all columns. Like this portion of your array, if you want to pick it up, and like this, suppose if you want, like you can build any complex indexes by using this numpy's arrays. Right now similar way, suppose if you want to, so now these are the functions like um, some. So suppose these, there are some functions which take an axis also as an argument. Like if I, in my numpy arrays, if I just call some function, right, so it will just add all elements of my array, and it just gives us a result. Now suppose if you want to do row wise summation or column wise summation, right, suppose if you want to do a column wise summation, then you can specify dot sum axis is equal to 0, then all rows will be added, all columns will be added together, and you get a result. And similarly, suppose if you want to calculate sum row wise, then you can pass axis is equal to 1, and the element wise sum will be done. Then, and similarly, you can find max, min, standard deviation, like on the entire array, or row wise, column wise, or any other combination. Right, so then the matrix operations also, by default the operations are element wise. Like you need not write loop. Like if you have two matrices of the same shape, right, like in A and B, then if I just write A plus B, then all elements will be added element wise. Right, so like here you can see that these two matrices are added, subtracted, multiplied, and other things can be done quite easily. Like similar with this, if you want to add any scalar to all elements of your two-dimensional array, like in the one-dimensional, same way. Like suppose if I want to divide every element of this matrix by 9, so I will just write by 9. So internally, this 9 will be broadcasted to the shape of this matrix. Then the division will be performed. Like this, we can do all other operations like -1. So this is what we call broadcasting in numpy's array. Like this min, max, all other functions, that they take axis also as an argument. So this was about two-dimensional array. So now the same idea is extendable to three-dimensional array. Now when we stack multiple two-dimensional arrays together, then we create a three-dimensional array. Right? Now, like how do we create a three-dimensional array? We can just club multiple two-dimensional arrays together. Like here you can say that 1, 2, 3, 4, 5, 6, 7, 8. Like we have created a three-dimensional array. Now for accessing any element of this three-dimensional array, now we need three indexes. First index, like from which two-dimensional array to pick up, like from the first one or second one, and the second is which row number and column number, as in two-dimensional arrays, right? So now if you see the shape of this array, it will be like 3, 2, 4, or whatever it is. How many number of two-dimensional arrays you are stacking together, that will be the dimension or elements along the zeroth axis. Then rows and columns will be the second and third dimension. Right, so like this, you can suppose if you wish to create an np.0 3, 4, 5, it will create an array like this. So three two-dimensional arrays, three 4 cross 5 arrays stacked together. Right, so like this we can create arrays. So generally when you see a satellite image or any simple image, or if the image has a single band, so the image will be represented as a single two-dimensional array. When our image is RGB or it contains more than one band, right? So then the image will be generally represented using three-dimensional array, right? So every dimension or every two-dimensional array will be representing a channel. Like one may be red, green, or blue. So that we will discuss in detail in the subsequent lectures. So indexing is also a similar way. Like now for accessing any element of the three-dimensional array, you need now three indexes, like 0 for first x-axis, like from which two-dimensional array to pick up, then row number and column number. So this was the basic idea about numpy array. So we will be manipulating these, like our image ultimately will be represented in a numpy array, and then we will be manipulating these things in our future course or future lectures. Then the second library I will briefly touch upon is the matplotlib. So matplotlib is a Python plotting library that produces, you can say, multiple is used for producing publication quality figures, and it's quite easy to use. See, actually, but for plotting, for if you wish to learn numpy, actually then you must have some basic idea about numpy arrays. So because matplotlib works on numpy arrays. So this is the overall anatomy of a matplotlib chart. You can say that the entire thing is called a figure, right? So in the figure, the drawing area, the entire canvas is called a figure. So in the figure, we can break into small pieces that we'll call axes, and like if you want to inside that, if you want to create multiple subplots, so that we'll call axis, and these are the axis, x-axis and y-axis are the axis, and these are markers and all you can put on the plot, right? So now actually there are two ways of creating figures in matplotlib. One is we explicitly create figures, like first we create a canvas, and on that canvas we keep on adding new and new axes, right? And then there is another way where matplotlib automatically take care of creating these x. So we just keep on calling the plot function, so matplotlib automatically takes care of this, creating this axis and adding that to the figure. And so I will just explain you both of the ways. So one first thing what we will do, we will explicitly create figure and subplots or axis inside that. And the second way we will see that both of have some pros and cons that you can just read about the documentation, and depending on your requirement you can follow either of the approach. Right. So for using matplotlib, first you need to import matplotlib to your first install. Then so pyplot is the package which generally is used for plotting. So this is the convention, matplotlib.pyplot, we import it as plt, right? So now here what I am doing, I am creating now two one-dimensional numpy arrays. So in one I am storing the range, I am storing the numbers from 0 to 10, so that may be some angle, and in the y I am just calculating the sinusoid of that value, maybe if it is a radian, so I'm just calculating the sinusoid of that. Now here if you see x and y, I have two values, one containing the x, and in the y-axis suppose if I want to plot the sinusoidal of that, sine of that. So suppose if I want to create figures and axis explicitly, then what I need to call? I need to call the function plt.subplots. It returns us a figure and axis, and then on that axis we can plot x and y. So here x and y I am passing, both of them are one dimensional arrays. So if I plot this, so you can say that a nice plot like this is created quite easily. So x, but only thing that we need to pass it to one dimensional arrays. So right. So now suppose if you don't want to create these figures and access explicitly by calling plt.subplot, then you can, otherwise you can call directly plt.plot as well. So plt.plot automatically creates the figure and adds access to that. So in the previous case we were explicitly creating these things, here it implicitly creates and keeps on adding that. So this way also you can do. Now similarly, suppose if you want to add two series together in your plot, that also can be done quite easily, 2, 3 and more, think whatever you wish to do. Then you can create multiple subplots as well by using, like, the horizontally you can arrange them, vertically you can arrange, and whatever is convenient for you, right? So then the next part of this is, suppose now this is, we have tried to plot one dimensional arrays. Now because as we said that because our images ultimately are represented as a matrix of cells, right? So suppose if you want to represent, because these two-dimensional arrays cannot be plotted using plain plot function, right? So for that NumPy offers a special function called IMShow. So IMShow can be used for drawing an image on the screen. So for today's session, I will just read a simple JPEG image directly using Matplotlib only. So from tomorrow onwards, actually, we will be using a specific library called JIDAL for reading and writing images. So that so today, because I just wanted to get you familiarized with the just plotting the image, visualizing the image, because tomorrow onwards we will be directly visualizing the image. But for reading the image, we will use a different library, not Matplotlib, because Matplotlib can just read few formats only, right? So it cannot read a geotiff where coordinates are also stored with an image, right? So Matplotlib have as an function called MP image, right? So that can be used for reading an image. So actually in my Google Drive I have stored already this sangam.jpg. There is an image that actually I will share with you all. So first thing, because that is available in my drive. So first thing, if you want to do drive, you need to mount your drive to your Google Colab. So for mounting that, you need to just go here, click on the folder icon and just connect Google Drive. So with that, Google Drive, it asks for permission. You just allow the permission. Then your entire Google Drive gets mounted to your Google Colab. And so the drive got mounted here. If I refresh it, so you can see drive inside that the data is available. Now I directly will go to the data part where I left. Right, so for reading the function, there is a function called IMRead. So IMRead, if I read, so it just gives. Now if you see shape, because now you see, if you see the shape, this is in the format called HWC, height, width, and the channels. Right, so the, because as we said that because this is a colored image, it has more than one band, so it is represented as a three-dimensional array. Right, so now suppose if I want to show a see this image, so now we need to call the IMShow function. Right, for just plotting one dimensional array, you need to call plt.plot function, but when you want to display a two-dimensional array or an image, at that time we need to call IMShow function. Right, so if I call plt.imshow, here you can say that the image gets displayed on the screen. Right, so tomorrow onwards we will uh, cover this in much detail, but we will not read the image using NumPy. For the time being, you can just remember that for plotting a two-dimensional array or an image on the screen, we need to use the function IMShow. Right, so similar way, suppose if you want to, like this is a three-band image, you want to extract an individual band from, like suppose if I just want to extract red band image, right? So then from the three-dimensional array, I want to extract the pixels of a red band only. So this indexing, you can just go through this indexing. So with this, with the help of this index, I am just what I am doing. And for the channel 0, I am extracting all rows and columns. Right. So like if I plot this, so this is just a red band extracted from that image. Now if I just want to show it in a grayscale, then I can just say CMap is equal to gray. And grayscale image is shown. So similar way, you can plot all these bands together as well, like red, green, and blue separately. If you see these red, green, and blue bands of our image look like this, right? So with that, I come to the end of my demonstration or hands-on. So I'll just briefly touch upon like what we have discussed till now. So we basically discussed about NumPy array. So NumPy array is NumPy is a or numerical Python is a library for handling n-dimensional numerical data, right? So it offers multiple or more very efficient ways of creating and manipulating multi-dimensional arrays, right? So then we discuss in detail about how do we create a vector or say one-dimensional array. Then we discuss about the different indexing different ways of indexing that data. Then we extended it to two-dimensional arrays, then three-dimensional arrays. Then we briefly discussed about the matplotlib library, right? So as we discussed, there are two ways of creating a matplotlib lab. One is either we use explicitly called plt.subplots, or otherwise we just call plt.plot, let it manage the entire thing, right? So if with this I come to the end of this session. So if you have any questions, please post them on the chat, so I will try to answer them to the best of my knowledge. So thank you very much.